Good day. In the previous lecture, we introduced sequences, some of their properties, and ways of determining whether these sequences converge or diverge. For today's lecture, we will look at series, which are sums of terms of sequences. We will discuss methods for computing the sum of an infinite series, and we will also look at ways of determining whether a series of constant terms converges or diverges. We first define an infinite series. An infinite series is an expression of the form summation of a sub n, with n ranging from 1 to infinity, which is equal to a sub 1 plus a sub 2 plus a sub 3, and so on. The numbers a sub 1, a sub 2, a sub 3, etc. are called terms of the series. Now, for our notation, if there's no ambiguity, we may write series by omitting their indices. Now, our main goal for today is to determine whether the sum of a given infinite series, summation of a sub n, with n ranging from 1 to infinity, exists. Now, we will look at what we call partial sums of a series. So given an infinite series summation of a sub n with n ranging from 1 to infinity, we consider the following. First, we have s sub 1 equal to a sub 1, s sub 2 equal to a sub 1 plus a sub 2, which is the sum of the first two terms. S sub 3 is equal to the sum of the first three terms, a sub 1 plus a sub 2 plus a sub 3, and so on, where S sub k is equal to the sum of the first k terms of the series. For all non-negative integers k, the finite sum S sub k equal to the summation of a sub n with n ranging from 1 to k is called the kth partial sum of the series. These partial sums will play a huge role in classifying the convergence of a series. Now, let's look at the following definition. So suppose we have S sub k denoting the kth partial sum of a series summation of a sub n, then the series is said to be convergent with sum capital S if and only if the sequence of the partial sums converges to S. In this case, we can write the summation of a sub n with n ranging from 1 to infinity equal to S. We also define what it means to be a divergent series. So a series is said to be divergent if and only if the sequence of partial sums diverges. For example, if C is a real number, let's show that the constant series summation of C with n ranging from 1 to infinity converges only when C is equal to 0. For the proof, we observe that the kth partial sum of the constant series is just equal to C added to itself k times, or simply C times k. In this case, if C is equal to 0, we have S sub k equal to 0, and the limit of S sub k as k goes to infinity is equal to 0. Hence, the constant series converges with sum equal to 0. On the other hand, if C is not equal to 0, then the limit of S sub k as k approaches infinity is equal to the limit of ck as k approaches infinity, and we have two cases here. This is either equal to positive infinity if C is positive, or negative infinity if C is negative. Thus, the constant series diverges. For number 2, we determine whether the series summation of 1 over the quantity n squared plus n with n ranging from 1 to infinity is convergent or divergent. To solve this problem, we will use partial fractions, so we get the partial fraction decomposition of 1 over the quantity n squared plus n. Observe that for all non-negative integers n, 1 over the quantity n squared plus n can be written as 1 over n minus 1 over n plus 1. Thus, s sub 1 is equal to the first term, which is 1 minus 1 half. S sub 2 is equal to the sum of the first two terms. We have 1 minus 1 half plus 1 half minus 1 third, and observe that negative 1 half and 1 half will cancel out, leaving us with 1 minus 1 third. Similarly, S sub 3 is equal to the sum of the first three terms, and looking at the addends here, we observe that some of the terms will cancel out, leaving us with 1 minus 1 fourth. And observing the pattern, we have S sub 4 equal to 1 minus 1 fifth. In general, S sub k is equal to 1 minus 1 half plus 1 half minus 1 third plus and so on up to 1 over k minus 1 over k plus 1, and cancelling out the additive inverses, we get 1 minus 1 over the quantity k plus 1. Hence, evaluating the limit of S sub k as k goes to infinity, we have the limit of the quantity 1 minus 1 over k plus 1 as k approaches infinity. And in these terms here, the denominator will go to infinity, which means this fraction will go to 0. So that gives us 1 minus 0 equal to 1. Therefore, the series is convergent with sum equal to 1, or we can write the summation of 1 over n squared plus n with n ranging from 1 to infinity equal to 1. For the next few examples, we will look at some special infinite series. For this example, that a and r be non-zero real numbers, our goal is to determine all values of the common ratio r, for which the geometric series summation of a times r raised to n with n ranging from 0 to infinity, which is equal to the sum of a times r, a times r squared, and so on. We want to find all values of the common ratio r such that this geometric series converges. Note that if r is equal to 1, then the series is a constant series summation of a with n ranging from 0 to infinity. Since a is not equal to 0, this series diverges. Now, suppose r is not equal to 1. We let the kth partial sum be equal to the summation of a times r raised to n with n ranging from 0 to k. For any non-negative integer k, we have the following. The kth partial sum is equal to a plus a times r plus a times r squared plus and so on up to a times r raised to k. Multiplying r to the previous equation, we have the following. And getting the difference, we have s sub k minus r times s sub k. And getting the difference on the right-hand side, notice that the terms here will cancel out, leaving us with a minus a times r raised to k plus 1. Subtracting the previous two equations and isolating s sub k, we get the following equation. We have s sub k equal to a times the quantity 1 minus r raised to k plus 1 all over 1 minus r. We then look at several cases depending on the value of r. First, suppose that the absolute value of r is less than 1, that is, r is between negative 1 and positive 1. Then, evaluating the limit of r raised to k plus 1 as k goes to infinity, since r is between -1 and 1, this limit will be equal to 0. Therefore, the limit of the kth partial sum as k goes to infinity is equal to the limit of a times the quantity 1 minus r raised to k plus 1 over 1 minus r as k goes to infinity. And since this goes to 0, the numerator will become a, giving us the limit a over 1 minus r. Hence, the sequence converges with sum a over 1 minus r. On the other hand, suppose that r is either less than or equal to -1 or r is greater than 1. Then, evaluating the limit of r raised to k plus 1 as k goes to infinity, we observe that this limit does not exist, since the magnitude of r will increase without bound as k goes to infinity. Therefore, the limit of the kth partial sums as k goes to infinity will not exist. This will not exist since this quantity will either go to positive or negative infinity. Hence, the series diverges. The following remark summarizes our previous results. So suppose we have non-zero real numbers a and r. The geometric series summation of a times r raised to n is convergent with sum a over 1 minus r if the absolute value of r is less than 1 and divergent otherwise. For our next example, let's determine if the summation of -4 raised to n over 6 raised to n minus 1 converges or diverges, and in the event that it converges, let's also find its sum. So to solve this problem, we will use properties of a geometric series. So first, observe that this series can be written in the following manner. We will just express 6 raised to n minus 1 as a product 6 raised to -1 times 6 raised to n. In this case, -4 raised to n and 6 raised to n have the same power, which means we can write the series in the following manner. We have the summation of 6 times the quantity -4 over 6 raised to n, with n ranging from 0 to infinity. And here we can simplify -4 over 6 as -2/3. Here we have a series, which is a geometric series, with first term equal to 6 and common ratio equal to -2/3. Since the absolute value of -2/3 is less than 1, the geometric series is convergent, and its sum can be obtained by using the formula. We have 6 over the quantity 1 minus -2/3, and simplifying this gives us 18 over 5. For the next example, the harmonic series is a summation of 1 over n, with n ranging from 1 to infinity. We will show that this series is divergent. So for the proof, we consider the graph of y equal to 1 over x. Its graph is shown in purple, while the blue rectangular regions have height 1 over n and length 1. By comparing areas for each non-zero natural number, we have 1 over n times 1 equal to 1 over n. This is the area of the rectangular regions. And note that these areas are larger than the area under the purple curve. In this case, the area under the purple curve on the specific subintervals are given by the following definite integral. We have the definite integral of 1 over x, with x ranging from n to n plus 1. Now, for each non-zero n, it follows that the kth partial sum is equal to the sum of the first k terms of the harmonic series, which is equal to 1 plus 1/2 plus, and so on, up to 1 over k. Now, this is greater than the sum of the following definite integrals. We have the definite integral of 1 over x on the interval 1 to 2, intervals 2 to 3, and so on, up to the interval k to k plus 1. And note that the summation of these definite integrals is equal to the definite integral of 1 over x, with x ranging from 1 to k plus 1. Evaluating this definite integral gives us ln of k plus 1. Now, the limit of ln of k plus 1 with k going to infinity is equal to positive infinity. We also have the limit of s sub k as k approaches infinity equal to positive infinity, since the kth partial sum is greater than ln of k plus 1. Thus, the harmonic series diverges.